My name is Amanjot Kaur. I am excited to be here today to discuss about my poster. Firstly, start with the overview. With the shift to electric vehicles, battery longevity and dependability have become crucial. Estimating the remaining useful life of EV batteries is essential for minimizing unplanned malfunctions, streamlining maintenance plans, and boosting user confidence. The non-linear and dynamic nature of battery degradation makes it difficult to handle using traditional estimate techniques. This study investigates the use of machine learning models for precise RUL prediction, including gradient boosting, random forest, decision trees, and linear regression. Now I am turning to aims and objectives. With the help of an existing Kaggle dataset, this project seeks to create a machine learning model that create forest how long electric vehicles batteries will last. In order to accomplish this goal, this study aims to review existing research on several battery technologies for electrical vehicles. The other is to research machine learning techniques that can be applied to the prediction of battery life. The third one is to create an artificial intelligence model that can forecast how long an electric car battery will last. And the fourth is to use accuracy metrics like mean square error, R squared, and RMSE to assess the machine learning model's performance. And next, um next is iteration, predicting the remaining useful life of electric car batteries accurately is crucial for increasing battery lifespan, lowering maintenance cost, and improving operating reliability. Complex patterns of degradation cannot be accurately captured by traditional approaches. This study uses machine learning models to enhance prediction accuracy and facilitate more intelligent battery management. And now I am turning to literature review. The EV market is dominated by lithium ion batteries because of their high energy density and extended cycle lifespan, whereas lead acid and nickel cadmium batteries have lesser efficiency and raise environmental issues. Data driven approaches have become more prevalent in predictive maintenance. According to recent research, machine learning models perform better than linear or physics based methods, especially ensemble approaches and deep learning hybrids like CNN, LSTM. Ne- Nevertheless, issues including computing demands, uncertainty estimations, and model generalization continue to exist. The next is methodology. There was a quantitative method we used to publicly accessible batteries datasets with the RUL labels, voltage profiles, cycle index, discharge time, and changing time. The phases of the research were organized using the waterfall framework. The first, like, review of the literature, data gathering and publication, creation of the model, training, performance, assessment, discussion, and finalization. Four models were implemented in a Jupyter notebook using Python, linear regression, decision tree, random forest, and gradient boosting. Strong evaluation was granted using cross validation methods. Now I am turning to research outcome and discussion. Despite achieving an R2 value of 0.984 Linear regressions did not perform well on compilating patterns through um, they run the risk of overfitting. Decision trees offered a little increase in accuracy. Random forests R2 of 0.995 and MAE of 2.13 showed outstanding performance. With an R2 of 0.996 and MSE of 0.008 and an RMSE of 3.79, gradient boosting excelled above all others. According to patterns seen in literature, assemble models like random forest gradient boosting were better at capturing the non-linear battery degrading characteristics. Although it took longer to train, gradient boosting produced very accurate predictions thanks to its iterative error minimizing. Among the risks that were expected were model underperformance and data availability. Alternative models techniques, backup storage procedures, and dataset redundancy were all part of the mitigation. Effective giant based time management and Google Cloud computing were used to overcome resource, hardware, and time constraints. The next is conclusion. This study shows that sophisticated machine learning algorithms provide extremely accurate RUL forecasters for EV batteries, especially gradient boosting. The key to success was rigorous model validation, well organized project, and efficient feature selection. Future research should investigate uncertainty quantification, deep learning hybrids, and real time BMS integration to enhance the useful of deployment in the EV sector. And the next, ethical considerations. This research was conducted using publicly available battery datasets, ensuring no provisional or sensitive human data was involved. Data users complied with open source license agreements, and all datasets were handled responsibility to maintain integrity and transparency. Ethical research practices were followed throughout the project, including proper citation of sources and adherence to academic honesty. Since no human participants were involved, formal ethical approval was not required. However, careful attention was given to data privacy, accuracy, and responsibility reporting of results. Thank you, sir.